We are now going to learn about another interesting concept in optics that's called shift. Shift is twofold. One is called lateral shift, another one is called vertical shift. Let's quickly understand what is meant by shift and then we can start with the experiment. Now, imagine you are supposed to travel in this direction. Let's say you're supposed to travel in this direction, and because of some reason you shifted your path and went a little sideways in this direction. So this is your original direction and this is your new direction. So the gap between original and the new direction is called shift, and in this case, since there is a sideways movement, we call this lateral shift. This lateral shift we can experience clearly when we use a rectangular glass slab. So I want to describe the ray diagram, and after that it should be very clear to you. Now let's go ahead and understand what that shift is. Imagine this is your rectangular glass slab. Outside we have air, inside we have glass. And again, outside is air. Please think which is the optically denser material and which is the optically rarer material. We already know from our previous discussions, glass is the denser and air is the rarer material. Now, let's imagine there is a light ray that travels and hits this particular glass slab at a certain angle. Now, we already know this is the interface, and at the interface we need to draw a normal perpendicular to the interface. So this is our normal, and we can label this as O if you want. Now, try to recollect from our previous experiments. Light is traveling from rarer material into denser material. Will it travel straight without deviation or will it bend towards the normal? Try to recollect. It always bends towards the normal. As you can see, instead of going in a straight path, it is bending towards the normal. So wherever it touches, I need to draw a new surface. So let me do that. I want to correct this a little, and I want to make this wider angle to give more clarity to our discussion. So I'm taking a wider angle, right? And because of that wider angle, I can give you more clearly that deviation. Alright. So as you can see, outside it's a larger angle and inside is a smaller angle, indicating that light bent towards the normal, right? Now wherever it touches, I again have to draw a normal to this surface. Let's label them as A, B, C and D. So light through the glass slab touched the CD surface. So on the CD surface, I am drawing a new normal. And look at this carefully. The angle that you see over here and the angle over here will be the same because you are operating between two parallel lines. Okay. And now this time light is traveling from denser medium to rarer medium. So please remember, will it be towards the normal or away from the normal? It will be away from the normal. As here you had towards, here you would have away from the normal, and that would be my emerging ray. Let me define these terms. This ray is called the incident ray because we are sending it into the glass slab, and this ray is exiting the system, it is leaving the system. We call this emergent ray. Now observe carefully. If this glass slab doesn't exist, imagine there is no glass slab and you are projecting laser, then this laser would have traveled straight in this manner without any deviation. But because of placing this glass slab, instead of going in this direction, it shifted sideways towards this side. So this sideways shift is called lateral shift. One more time, listen carefully. This is the original path of the light. rarer to denser towards the normal, denser to rarer away from the normal. But what I want you to do is imagine that this slab doesn't exist over there and you're just projecting light on this board. Then light would have traveled straight without deviation. So this would have been its path. So instead of going in this way, because of the glass slab, it had to shift to the side. This sideways shift is called the lateral shift. Now we are going to do this accurately on a paper using a glass slab, and then we'll also use a laser light to confirm all this. So let's go ahead and work about this on the glass slab. But before that, there is a small observation table. It's just couple of points. Lateral shift is one of the columns and incident angle is the second column. So let's try one angle and then we'll explore the remaining. Now let's look at the materials that we need for this experiment. We need a rectangular slab, we need a paper, we need few bell pins, I need a protractor, I need a set square. This will help us in finding the distance between two parallel lines. And then I need a drawing board or a soft rubber board. Now, I would like to show you the step-by-step procedure now. Right. So before you start, I want you also to label your paper if you're working on this experiment. My name is Bhanu Prakash, so I'm writing my name over here. And then I'm also writing the incident angle. Incident angle, I want to choose 40 degrees for this experiment. Now, please observe, I'm placing this rectangular slab in the middle of the paper. Just make sure that there is enough space on the top and the bottom. Now, draw the boundaries carefully. And label the boundaries as A, B, C and D. On the AB side, select a point a little close to A. Don't select it midway. If you select the point midway, there's a good chance the emergent side or emergent ray would cross the C, the corner. It would be very tough to observe from the corner of the glass slab. So preferably keep it somewhere close to A. You can label this point as O. At this point, we need to draw a normal. For that, I'm going to place a protractor. Right? So let me turn it around so that you can observe this clearly. I have this point. On this point, I am matching the origin of the protractor and the 0, 0 line is matching with the AB line. Now at 90 degree, I am making a new point. So I have an origin point, I have a new point at 90 degree. I am using the same protractor to join them to form my new normal. I am using a dotted line as normals are imaginary lines. Now, this is the normal. And if you recollect from our previous discussions, normals are labeled as 0 degrees as they are reference lines. These lines are reference lines. That means all angles are measured from these lines. Now, if you remember, our incident angle is going to be 40 degrees. Now, this is a little tricky. Please observe this. In a protractor, there are two lines, most important lines. One is the 0, 0 line, other is the 90 degree line. Here we have 0, 0 line, here we have another 0, 0 line. So I just want to match 0 degrees with the 0 degrees. So please observe what I am doing. I am matching 0, 0 line with the normal line and I am matching the origin with this point O. So as soon as I do that, whatever point, the 40 degree point I see, that will be my incident ray. I will explain it one more time, do not worry. Let me draw this first. Since this is an incident ray, I want to use an inward going arrow. One more time, let's try to find how I drew this incident ray. This is a 0 degree line. So I have to place my protractor 0 line on this 0 line. And this is the origin of the protractor. This is the origin of our system. I'm just matching the origin with the origin. And then I'm matching 0 degree line with the 0 degree line. Then I get the 40 degree location. Okay. Normally, whenever you are finding angles, your regular habit is to place the protractor in this way and find it. But that is wrong, because here you are matching 90 degree line with the 0 line. So this is a very, very important distinction. Now the next step is, I'm taking this rubber sheet board, I'm placing this paper on top of the board, and then I'm poking 2 points or 2 pins on the incident ray. The most important condition for this particular step is the 2 pins should have a gap. If they are placed too close, it is as good as taking a single pin. So since we are using 2 pins, they should be far apart. 2 or 3 centimeters is fine. And don't keep them too close to the edge of this rectangular slab, the AB or CD. If you keep them too close to the edge, then moving that glass slab will cause disturbances in the pin. Make sure the 2 pins are vertical. They should not bend around. And also, when you are observing these pins using a glass slab, try to observe the base instead of the heads. So bases cannot move, but the heads might tilt around. Then the next step is, wipe the edges of this glass slab cleanly to avoid any fingerprints, and then place the glass slab in such a way that the incident side perfectly matches. Due to some manufacturing defects, the other sides might not match. Do not worry about it, or you can just draw a new line on the CD side to make sure that you're doing it in a proper way. So I drew a new line because the old one was not matching with the new one. But always remember, incident side is the most important one. Now I want to raise this entire setup to show you the next steps. Let's go ahead and do that. Now let's observe how to see this. The pins are on the AB side and CD side is the emergent side. The way you do it is, close one eye and observe the 2 pins through the glass slab using your second eye. Rotate your entire arrangement slowly, and in one particular angle, you will see both the pins appear in a straight line. This is the most important step. One more time. Right now I am observing inside this particular glass slab. I can see both the pins. They are at separate locations. They are not in a straight line because I can see both of them separately. Now what I am doing, I am turning it around until I see both of them in a straight line. The next step is poking 2 more pins, but before that I want you to experience this. Seeing both the pins in a straight line is a very important step. Let's go ahead and see that in a zoomed in version. Now observe the 2 pins inside the glass slab. They are separated out. I'll slowly rotate it and I'll stop as soon as you feel that both are in a straight path. All we have to do now is poke 2 more pins in this direction. I will poke the first pin, then I will show you again in a zoomed in version. Now I have the 3rd pin. I am poking them on the CD side. So observe what I am doing. I am rotating until I see both the pins in a straight line. That means my eye and the 2 pins are in a straight line. I am taking the 3rd pin and I am poking it on the CD side so that all 3 pins and my eye are making a straight path. It seems almost perfect. Now I want you to observe this in a close-up manner. Now observe the 3 pins are at different locations. Now rotate the board slowly until all the 3 form the same straight path. Now please observe, we have 4th pin. This is the 4th pin that I just placed. All 4 are appearing in different locations. Now let's rotate it and find the correct position and see if all the four are making a straight path. As you can see only the last pin, the other pins are hiding behind it. It means all the four are in a straight. So let's label these pins before we could proceed. I can use the incident side pins as E, F, and the emergent side pins as G and H. Now I'll put the glass slab to the side. I'll remove all the four pins. I'll put them to the side. I don't need the rubber sheet board anymore. Now the next step is making sure you label the G and H perfectly. Then I'm taking the protractor to join this G and H until they meet on the CD surface. Alright? So this is your emergent ray and they are meeting on the CD surface. What I'll do now is I'm making a point on the CD surface, and from there I would like to draw the normal. The way we draw normal is just like before. I'm matching CD surface with the 0, 0 line of the protractor. So one more time, please observe. This is the CD surface, the new surface, the old one was a mismatch. Now the 0, 0 line I'm matching with the point, and this is my 90-degree location. Now I'm connecting these 2 points. I can call this point as O dash. I'm connecting O dash with this new point using a dotted line as it is our new normal. So this is the new normal. Now let's measure this angle. This is our emergent angle. This is our incident angle. We already know incident angle is 40 degrees. Let's check the emergent angle. Now here we have the emergent angle. This is our incident angle of 40 degrees. As before, normals are always 0 degrees. And in our protractor, this is the 0, 0 line. I'm just matching the 0, 0 line with the 0 degrees, and I'm matching the origin of the protractor with this particular point. And when I do that, I can clearly see that the emergent angle is 41 degrees. It's not exactly 40 degrees, it's a little more. Sometimes it could be human errors, or in some cases it could be errors due to the manufacturing of the glass slab. It could be anything. Anyway, this emergent angle that we have just seen is 41 degrees. It's alright, that's not a big concern for us. Now, our job is to find the lateral shift. So this is our incident ray. Because of the glass slab, instead of going in a straight path like this, the ray shifted sideways. Let's check how much it has shifted. And for that particular reason, I'm going to extend my incident ray. See this EF? EF is my incident ray. With this set square or any scale, you can use it, and you can extend your incident ray like this. See from here. I'm extending it further. If you have done a good job, then there is a high chance that you will see the extended incident ray and the emergent ray as parallel to each other. As you can see here, they are very perfectly matched parallel lines. This is my extended incident ray. This is my emergent ray. All I need to do is find the shortest distance between these two parallel lines. So for that, we use an instrument called the set square. Very simple to use. The set square has two legs, obviously, perpendicular to each other, 90 degrees. Set one of the legs on one of the parallel lines, and the second line will give me the value. If you could observe this carefully, the first line is arranged on one of the legs, and the second line is showing me 1.7 centimeters. See, this distance from here to here is 1.7 centimeters. That means lateral shift, Lateral, lateral shift is 1.7 centimeters. That's it, people. This is the entire experiment where we have proved that the light ray shifted by 1.7 centimeters to its left when you pass that light ray into a rectangular glass slab. Now let's get back to the board and conclude this experiment. Now we just completed the experiment, and for 40-degree incident angle we found lateral shift to be 1.7 centimeters. Can you guess what would be the lateral shift if the angle is 0 degrees? In fact, if the angle is 0 degrees, let's imagine a scenario where angle is 0 degrees. Now, this is the 0 degree line. That means this itself is the incident ray. When you put two pins and observe from the CD side, you would exactly see the next two pins in the same path. The reason is, since there is no refraction along the normal, you do not see any variation. So for 0 degrees, the lateral shift would be 0 centimeters. Shift only happens when there is an angle of incidence, right? Now, we are done with the experiment. I quickly want you to understand what factors does this lateral shift depend on. So clearly you can see the table. It does depend on the changes in incident angle. As incident angle increases, lateral shift value also increases. Another factor it depends on is the type of the material. For this glass, at this angle, we are getting 1.7. If it was a different type of glass, you would see different lateral shift value. And another last one is the thickness of the glass slab. For this experiment, this is the thickness, this particular distance. If I would have increased the thickness, then the lateral shift will increase. If I decrease the thickness, the lateral shift will also decrease. It's wonderful that we analyze this experiment, but I want you to get the essence of its practical applicability. Lateral shift is a very, very important concept in designing the windshields of the cars. You have the cars where the driver sits, right? And in front of the driver, you have a windshield, a glass shield. Now think about it. If the glass shield is too thick, then the shift would be enormous, and because of that enormous shift, the judgment by the driver would be wrong. That could result in accidents. He might feel that the person on the road is at one location, but the person might actually be at a faraway distance. So that would cause accidents. So that's the reason windshields glass surface are very, very thin. They can't keep too thin because it might crack. But if they keep it of considerable thickness, then the errors in judgment can be avoided. So with that, we are done with a very beautiful concept called the lateral shift.